Okay, I think we can go ahead and get started. So this is Dr. Darren Homrighausen, and he is a professor of statistics at Texas A&M. And his talk today is Statistical Foundations of Data Science. I wanted to remind everyone that this meeting is being recorded. And with that, I'll hand it off to Dr. Darren.
All right, everybody, thanks for spending your afternoon with me. This is a topic that I think is incredibly useful and even more useful or more than useful. It's also, I think, really approachable, and it's used every day around the world in just so many different contexts. So what I want to try and convey today is that with a few techniques that we can derive from kind of classical statistical methods, we could make real world decisions in really important applications, say in business, but I'll be talking about it from an educational point of view. So I'm going to give a working example, and kind of at the end, I'll critique it a little bit so that we can learn a bit from that example. But it's going to be just one particular special case of a really broad framework under which you can use these types of methods in order to inform your decisions in practice. So like I said, introduced, my name is Darren Homrighausen. You can feel free to call me Darren. I'm a faculty here at Texas A&M in the statistics department. So we're going to just give a little bit of an introduction to a classic problem that many businesses, but any entity that has, say, a website goes through all the time. And we'll talk about some kind of background, the statistics that we're going to need. The underlying problem is about like two design decisions. So we're going to decide like how can we use statistics to decide which design is better? And then how can we use statistics even further in order to inform the experiment that's going to help us decide which design is better? So that's the overall framework under which we're going to be exploring these topics. So let's think about kind of a general framework for trying to solve problems in the wild, as like I call it. So that just means you're at a particular, you're out working, or you're in a classroom, or you're even just in your regular private life, and you have some sort of a problem confronts you. What's kind of a set of steps that we can take? And then I'm going to instantiate these into a particular problem that we'll be interested in solving. So we need to define like a research question. So, you might kind of have figured out that there is an issue, but you need to really carefully phrase it in terms of a question, form some hypotheses about these questions, identify appropriate tools that you can use in order to make measurements, say, because we can't do really anything until we can make some sort of measurements about the underlying phenomenon. And then we have to decide how we're going to measure that underlying phenomenon once we have our measurement techniques. So how are we going to decide, what does it mean for something to be large? Like what units are we going to use? That sort of thing. We need to set up and run an experiment. And once we've set up and run an experiment, we'll collect data, analyze those results, and we need to share those results and make decisions. So that's kind of the underlying framework if we were to be very generic. So what I want to do is when we go through each one of these steps, I'm going to just kind of describe these under this special case of where we have a particular type of problem, which is usually called a user experience or UX type of problem in practice. So UX is a very common acronym you'll come upon if you're looking into, say, web page design or anything to do with ads, or anything like that where you're trying to make some sort of a customized or like a beneficial user experience. So UX uses all sorts of tools in order to try and identify how well their whatever their application is being received by the user. So it could be, how successful is the user? How long does the user stay online? There's lots of different ways that we can phrase it. You can do this via interviews. You can do broad-based surveys, focus groups, or website analytics, like through, say, Google. So our goal is overall, like not necessarily like how do we just squeeze every last dollar or every last minute of eyeball time from the user, but we want to really make the world better by improving efficiency or accessibility, say. That's the kind of the framework that I'm looking at it from. So we're going to look at it under the general idea of website analytics. So website analytics is kind of like a suite of automated tools that you can use in order to try and describe how well some, say, design decision for a website is being received. And this could have a lot of different applications, ads or search or something like that. So we're going to talk about a particular one. So this was at a university, Montana State University, and they had a library homepage. And this library homepage had, the typical things libraries would have. You can search for an article, you find materials, request service like information or something, and then you can interact with the library itself. So there was these 3 tabs there at the bottom. And when the library was decided to kind of investigate, like, how well is this website really serving the university community? So they're not trying to make money off of this. They're really trying to help people be efficient with finding the resources that they need from this web application, which in this case is a website. So they tracked this for a while, and this is the same website. You'll notice that there's these kind of 5 buttons right here. These 5 buttons are just different pictures. So we're looking at just a different picture on the website, but it's the same overall website design. And through this kind of Google Analytics engine or application, you can track like where are people tending to click on your website, and where are they spending their time. So in this case, people were, and this is like a little heat map where the redder it is, the more people are clicking, and the bluer it is, the less often people are clicking. So people are clicking at the category search, they're clicking find a lot, request a lot less. They're even clicking through all these different pictures that the website has that kind of crawls across. But what they're rarely clicking on is interact. And so this caused the library to be a little bit curious as to maybe we're underserving the university interests, because there are really useful things that occur when you click on interact, but nobody's clicking on it. So then the question became, why aren't people clicking on it? And is there anything to be done that would encourage people to click on it, and hence hopefully increase their engagement, help them find the resources that they're looking for, and then we could kind of just better serve the community in that way. So that content category interact was hardly used. And it doesn't necessarily mean that it's underused, but just it seemed to the kind of subject matter experts that the topics that were contained within the interact tab should have been more useful than the proportion of users that were actually attempting to use them. So they decided we either need to get more traffic to that item, which would be kind of like a minor design change, or maybe eliminate the item altogether and reapportion all those tasks into other tabs, which would be a major design change. So perhaps maybe we can just kind of think simply, like, let's just start off with a simple change and see if that can help fix the problem. So maybe another category name is where the problem lies. So they did a survey, like a preliminary survey, and they looked at users and asked them several questions, but one of the questions was like, did you click on the interact tab? And if not, were you looking for these items? If you were looking for those items, which were under the interact tab, why didn't you click on it? And so people were like, connect is too vague, too close to interact. I don't know. I didn't know that about was under interact. And so they started to kind of notice this theme that this word interact was perhaps just not the right word to use. And it would be an extremely easy and minor change and hardly disruptive to the user experience if we just swapped out that word for a different word. So they brainstormed some different alternatives: connect, learn, help, services. And the goal at this point is, how do we decide which one of these words might have a better user experience? So we could use subject matter expertise perhaps, or we can argue about it, or maybe just come to some consensus decision. But in some sense, the best possible way would be to let the community itself determine what might be a better word choice. And the way that we can do this is with an experiment, and then do some sort of a statistical analysis to detect which one of these is going to be better. So we need to identify appropriate tools. and define metrics. So the tools that we're going to use, well, we're going to get website analytics through Google Analytics. And that gives us those like heat maps, but it also gives you this tabular array of data that has the number of times that all of these items were clicked in every user interaction with that website. So now we need to decide, what do we mean by a particular metric that we're interested in? So what would it mean for this to be a well-used tab on a website? So it could just be kind of the classic ad-based one, which is called click-through rate. Often it's actually written, through like THRU, but I've written out the kind of long form of it. But click-through rate is just how many times do people click on something on that website. So that would be kind of directly what that heat map was measuring. So drop-off rate measures the percentage of users who might leave a site from a given page. So if you click on interact and then you close that tab quickly or don't do anything after you click on it, there's some indication that you didn't actually want to go to that tab. And since you didn't get what you needed, you kind of got frustrated and you left the site altogether. So this, of course, has applications for ads, but it has applications in our current experiment here we're trying to run. Maybe the most relevant would be homepage return rate. So if you click on interact and then you ultimately go back to the homepage, the kind of idea would be that you didn't find what you needed under interact and you kind of went to the beginning. So it's kind of like drop off rate, but instead of dropping off, you've returned back to the home page. So these are three of the most commonly used metrics that I've seen in practice. So we need to decide, what does it mean to have a success here? Like, what does it mean for us to measure a well-used tab? We have to choose some sort of a metric. We have to choose a tool by which we're going to actually acquire that data. So we need to set up and run an experiment. And at this point, the details are going to depend on whether this is a major redesign or a minor redesign. And so here we have to have a live library website. And if we either A, take the library website down or do a dramatic change to the design of the library website, the users are going to be in some sense disenfranchised. They're not going to find what they're looking for. It's going to be incredibly disruptive. And if you have a business, it's going to be doubly so, because you might have the very real risk of alienating customers. So we have to decide whether we want to do a major redesign or a minor redesign. So that's the virtue of trying this smallest possible perturbation that we can to the website and see if that helps the problem or maybe fixes it altogether. So if we're doing a major redesign, we would want to maybe just take incoming traffic and only send a small percentage of it to the new design. So then the vast majority of our customers or users wouldn't have their experience disrupted at all. If it's a minor redesign, it's just like a change in labels or different ads or different ad placement or something like that. It's not going to disrupt user experience too much. So then we can just randomize all incoming traffic to these different variations. So in this case, it would make sense to randomize all traffic because it's such a minor redesign. So here we have the original website where we had to interact. Now we're just going to take services in this banner and just kind of put it in for interact. So we would, if we were to run this full experiment, we would redirect all the traffic to these 5 different options. Okay, so that's the kind of underlying application that I'm thinking of here, but really it wouldn't take too much imagination to extend this to just all sorts of different types of questions that would be like this. You have a clinical trial for a new drug therapy. You have a new classifier for deciding whether or not someone's going to default on their credit. All of these things are kind of a similar sort of idea of how do we compare these 2 different options to each other and decide which one is going to be the most likely decision that's going to happen, or which one's going to be the most likely outcome, say. So we need statistics in order to decide between these in a principled way. So since our time together here is so short, I want to be able to talk kind of entirely about one thing as opposed to just a teeny bit about a lot of things. So that's why I'm going to reduce the scope of the problem just for our purposes today. There would be changes in degree, but not substantial changes in the overall picture if I was to generalize this to the entire problem. But so for right now, we're just going to say, let's compare two of the options, interact and services. Of course, since I know the whole picture, I didn't make just a random choice of picking services, but we're just going to compare two different options here. And we're just going to choose one metric, the click-through rate. I'm not trying to convey that this is the best one by any means, but I'm just trying to, we're just using this as an application in order to hopefully kind of see the bigger picture of how this can be applied in real world. So we want to decide two crucial things. Which option is better? Or maybe more particularly, is services better than interact? And then how long do we want to run this experiment? So how long are we going to be allocating users to these two different options before we kind of stop doing that? We want to make the decision as fast as we can because we want to roll out a better design at once, like as soon as we can, once we've identified it. But we don't want to make the decision too hastily and maybe swap in something that's not as good or replace the status quo with something that's just the same. But now we've kind of disrupted the user experience. So I want to alert you, even though I'm going to talk about them in this particular order, that's really for expository reasons only. It's actually the opposite order that you should be doing this from a scientific perspective. You have to decide how long you're going to run the experiment before you start to try and answer questions about which option is better. But just because this is a learning environment, we're going to actually talk about it in the opposite order because it makes sense to kind of learn in the opposite order. But you just have to keep in mind, we always decide how long to run the experiment before you actually run the analyses. So we're going to start developing some notation. You can't talk about these things in any sort of detail without notation. So let's say we're going to end up with samples. So these are going to be, each one of these is going to be a person. They're going to have logged into the library website. They're going to be randomized into two options. They're either going to be sent to the version of the website with interact as the banner or the version of the website with service as the banner. And then we're going to just watch that user and we're going to see, did they end up clicking on interact or did they end up clicking on services, depending on which version of the website they're on, or did they not? So if they do, if yes, then we're just going to encode this as a 1. Same here. And if they don't click on either interact or service, we're just going to code it as a 0. So it's going to be this binary kind of data structure that we're going to be talking about here. So it's only going to, we're only going to track if they click on it or they don't click on it. And we're just going to map that to a 1 if they click on it, which we kind of think of as an event. Or we'll call it a 0 if they don't click on it, so no event. So the total number of users or people that are going to get sent to the interact version of the website is going to be n sub I. Total number to services n sub s. And those might be the same or they might be different. So you need to kind of choose those. Okay, so we want to compare the proportion of visitors that click on interact versus services. So there's actually only one distribution from a probability perspective that you can define on a 0, 1, like a random variable, if I were to use the word. And that's the Bernoulli distribution. And it just says there's some probability P that the X is going to evaluate to a 1, which would mean that the user clicked on that banner, or it's going to be a 0 with the complementary probability 1 minus P that they didn't click on that banner. So that's going to be our underlying distribution that we're going to be using for this analysis. So statistics and probability are very, very similar. They use the same language and they really are both about quantifying uncertainty, but they're coming about it on a different way. So probability is about saying, like, suppose we have a certain distribution, what might draws from that distribution look like? Statistics is like, well, suppose we have draws from some distributions, what might have that distribution been? So they're really talking about the same concept, but they're going in kind of totally opposite direction. So we have to be able to talk about both if we want to talk about either, really. So there's going to be two underlying population parameters. There's going to be P sub I and P sub S. So these are going to be the true underlying proportion of times that a person would click on the interact banner versus a person clicking on the services banner. And so the underlying question might be, how do these proportions compare to each other? And in particular, is the services proportion greater than the interact proportion? That's what we're trying to decide here today. So we can think of this as being the arithmetic difference between these two population parameters. And maybe is it strictly positive or not? So we can estimate this. These are unknown kind of, think about them as underlying, we'll never know what these population parameters are. All we know is that we can draw a sample from the distribution that has those parameters, and then we can use those samples in order to maybe infer something about that underlying parameter. So here, since our data is going to be either 0 or 1, we're just going to add up all those zeros and ones, and then divide by the total number. And that's going to give us the proportion of times that someone clicks on each one of those banners. So if you take the sample average of a bunch of zeros and ones, you end up with just a proportion. That's the proportion of times that number of times click divided by number total, the total number of users that went to that particular website design. So that's what we're going to label as p hat. So that's the common statistical notation to say we have the underlying population parameter, like the true kind of quality in the sense of our metric of that underlying design. We don't know that, but we can approximate it or estimate it with the data. And so we're going to kind of let that parameter wear a hat to indicate that we've computed a value or a guess in a sense of that parameter based on some data. So we know p hat sub I and p hat sub S. We'll never know pi or ps. We're going to use p hat sub I and p hat sub S as our approximation. And so that means we can approximate the difference between those two parameters with the difference between the two estimators. So at this point, we're ready to lay down what I would call a scientific question. So maybe does using the word services get more clicks than using the word interact? That's the relevant scientific question. If we can answer this in the positive, then we would want to swap out services in that banner, and then we would be ready to address the next problem that we see with our website design. If there's no evidence to suggest that it's better, we need to go back to the drawing board and try and figure out a different way to direct attention to interact or, redesign the website altogether. So that's a scientific question. The language of actually doing science is really a statistical question because it all comes down to doing experiments, gathering data, and analyzing that data. So we need to somehow convert this qualitative scientific question into a statistical question. That's the order of the day right now. So we need to phrase this scientific question as a statistical one in order to decide which design might be better. So that's where we're at here. Maybe I'll pause for just a moment to see if anybody has any clarifying questions, or if it's a, well, we'll see. Does anybody have any questions that they would like to ask that clarify the kind of core foundations of what we're talking about today? Okay. Well, no pressure. We'll have plenty of opportunity to ask questions later. So let's start talking about the statistical foundations here. So the scientific question is the qualitative one about, is the click-through rate for services greater than the click-through rate for the interact? So I'll mention at the end how we can do that. In this particular case, we could do all the pairwise testing doing exactly the framework that we're doing here, but we would need to do a control for something known as multiple testing. So we would look at doing kind of everything like what we're doing here, but we would just need to kind of increase the evidentiary threshold for each one of the pairwise tests in order to extend this to the multiple option example. So the most common way of doing that is something known as a Bonferroni correction, if you've heard of that. But the key idea is known as multiple correction. So you would do exactly what we're doing here, but then you would apply an additional multiple comparison correction. Okay, so this is formalized via something known as hypothesis testing. So we've made a hypothesis and now we're going to test it, but we're going to just instantiate it into statistical terminology first. So what does it mean for there to be no difference between these two options? Well, that the underlying population parameter proportion of clicks for each one of these two banners are equal, or their difference is equal to 0. Those are the same things. Alternatively, though, we're going to think of this in a directed sense, but we're going to say, the interesting thing would be to decide that services has a larger proportion or underlying probability of clicking than the interact banner. So that would mean the arithmetic difference between the two is strictly greater than 0. And so these go under the monikers null hypothesis and alternative hypothesis, respectively. Sometimes people say alternate hypothesis, but of course that's not the right wording. So alternate means one and then the other. Alternative means is it this one or that one? So they sound similar, but they're different. So what we want to do is, of course, we're going to estimate the population parameters that are underlying our hypothesis. So just like our scientific question is about like the kind of true state of nature, the statistical question is about the analogous parameters about the true state of nature, and so they're unknown. So we have to estimate them with our two estimates, and then we form the difference of those two. But now we're computing something from data, and our sample was random because we kind of randomly are assigning to different treatment arms. We're kind of randomly getting different users into our website at any one day or throughout one experiment. So there's going to be kind of a whole distribution of possible estimators that we could have computed. So we need to somehow take into account this randomness. So what the key idea, and I've been teaching statistics for a long time, but the key idea that for me distinguishes people that have a good understanding of how to do these things and don't yet have a good understanding is just recognizing that this is a random variable and hence it has a distribution. So we can talk about its randomness via distribution. That's just sounds simple on its face, but it's just the biggest hurdle that I see that people have. So and think about that, meditate on that until that seems to be just almost self-evident. And then think about it some more because it's the biggest stick of dynamite, I think, in someone's understanding of how to do these things in practice. So the distribution actually is surprisingly complicated for these two for this object, the difference of these two sample proportions. But, and really the main workhorse of what makes so much of classical statistics work is this shining knight of a result known as the central limit theorem. We don't have the sufficient time or background really to describe what this is, so I'm going to just leave it as just a maybe mysterious probability result. But it just says that if we're looking at sums of things, of which a sample average is a special case, we can approximate its distribution with a normal distribution. Yeah. Okay, so it just says that even though the true distribution of this estimator that we're looking at is unknown, or at least complex, we have a good approximation for it. And that distribution is centered on the thing that we're interested in. So that's a good thing to know. It just means that on average, it's going to point at the underlying thing that we're trying to estimate. And it has some sort of variability, which we'll describe a little bit later. Note that there are some what are usually called regularity conditions here. We need to have a sufficiently large sample size for the central limit theorem to hold. So there are, general rules of thumb, and here's one of them that seems to work pretty well in practice. So I'll just leave that parenthetically at the bottom. But just for our purposes, we're just going to think about this random object that we're using to estimate an underlying unknown population parameter has a normal distribution with this is the kind of centered around the thing that we're interested in, and then has some, of course, variability given that it's random. So the experiment tracks click-through on Interact. So I'm talking about this specific experiment that was actually done. I wasn't consulting on that. I just kind of saw what we in statistics usually say a post-mortem, which means somebody does an experiment without consulting a statistician. And so all we get to say is what the experiment died of. We can't really say good things about it typically. So it's sort of like our little gripe about people not getting us in on the ground floor, because a good experimental design is essential. So this experiment tracks click-through on Interact for 2 weeks. And they got 3,714 visits, and there were 42 clicks on Interact. Services was tracked for 1 week, and they got 1,348 clicks or visits, and then 45 clicks. So these are the actual results. We'll revisit this at the end. It's not that this was like disastrously bad, but there was something that could have been done that was a lot better. And we'll see that at the end when we talk about a power calculation. Okay, so let's compute our statistics. We just have our sample average. So it's 42 over 3714. And so the underlying code, software infrastructure that I'm going to be using, it doesn't really matter too much, but I'm going to be giving some code for how to do some of these things in the R statistical software computing package. So that's what the red text by and large is going to indicate, is some code that you can use. So the question is, and I'm going to throw this out to the audience here, do you think we can use the central limit theorem approximation based on that parenthetical result from the previous slide? Does anybody remember what that regularity condition was and whether this satisfies it? Well, I'm going to say, yes, we can, but you should go check it out. And by that, I mean, once this is posted, then you should take a look at it and see if you can convince yourself that this satisfies that parenthetical regularity condition. All right. So we can also estimate the variance. I'm trying to kind of run the ragged edge between talking about too much detail about what things that people might not have expertise in yet, but there's still some kind of key underlying notation and results that I have to refer to. So, some things I have to talk about. So in particular, the variance of these two proportions, like the difference between the two proportions, can actually be written down exactly, and then we can estimate them. So that's what this estimator is going to look like here. So this just is like taking the variance of that p hat sub s minus p hat sub I here, and then plugging in for what we don't know, the things that we do know. So that's how we're getting to this result here. So in this particular problem, it looks like 0.000269 or so. And so if you look at the previous, you could compute this with all of the information that I gave on the previous couple slides. So you can do that to check that later. So now the way the hypothesis testing works, and really the way science in general works, is you say, the underlying philosophy is I'm at this current state for some reason. Like it's the current state of nature. It's just the way my current understanding is described by the null hypothesis. And I'm going to demand some evidentiary standard to move me off of this hypothesis. So that's the kind of general philosophy. So we're just going to say, that's tantamount to saying, I'm going to assume that the null hypothesis is true until that assumption becomes untenable. That's the idea. So if we suppose that the null hypothesis is true, and we use this estimate of sigma squared that I just wrote down up there, then I know exactly the distribution of my underlying estimator that I'm trying to use, the difference in the sample proportions. And so it's going to be a normal, and it's going to be a normal that's centered around 0. So that's what this distribution looks like. It has some spread based on this sigma hat squared, but the spread is actually very small if you look at that, kind of fairly small decimal number that I wrote down up at the top. So large values of p hat s minus p hat I, when I actually run my experiment, are going to make me say, whoa, all of my assumptions that including the null hypothesis assumption led me to believe that this random variable had a normal distribution that was centered at 0. And now I'm all of a sudden computing a value that's like way out here, say. I would say, well, man, it's not very likely that my assumptions are correct because I observed something that would be an extraordinarily low probability under all of those assumptions. Maybe it makes me rethink that the null hypothesis might be true at all. So that's the fundamental way that we take the scientific principles behind hypotheses and instantiate them into the statistical notions of hypothesis test. So we can take this and we can go very carefully in the direction of computing p-values and other things, but I'm just going to talk about it from an intuitive point of view at this point and say, well, what does it mean to be large? So I'm saying too large or large values would give me pause about about the veracity of the null hypothesis. What do I mean by large? Well, I'm going to look at the actual difference, the arithmetic difference in the p hats that I've computed for my particular data set here. And then I'm going to simulate from this distribution. And I'm going to say, how often am I actually going to observe something that was at least as large as the thing that I actually observed with this particular experiment? So that's what this R code does down here. Note that this line is just the R code version of this. So there's nothing there. It looks complicated, but all I'm doing is just writing down, well, really the square root of that. So I took the square root to just get the sigma hat instead of sigma hat squared. And then I'm just going to add up all the times that of 100,000 random draws from this distribution that I observed something at least as extreme as the thing that I ended up observing. And during this particular random 100,000 draws, I observed about one draw that was at least as large. So that means, in a sense, I had kind of a 1 in 100,000 chance of seeing what I saw, given that the null hypothesis is true. Not a very big chance. So that would likely, or essentially would, cause me to say the null hypothesis is probably not true. And I have evidence to suggest that the proportion of times that people click on the services banner is greater than the proportion of times that people click on the interact banner. But maybe I want to say something a little bit more precisely. Or really, maybe I want to just give a more concrete interval. Like I can say that I have evidence that one is larger than the other, but can I quantify that uncertainty a little bit more carefully? So that's how we get to something known as confidence intervals. So confidence intervals they really convey equivalent information to the hypothesis test that we just wrote down. But they give that information through like a different light. Like think of it as a different lens maybe. So instead of this harsh, do I reject or not reject the null hypothesis? Instead, I'm going to give an interval of plausible values. For that population parameter that I'm interested in, which is the difference between the probability of a click in the services banner versus probability of a click for the interact banner. And I find that I have a range of plausible values for this difference of something like 0.01 up to like maybe 0.03 or so. So that's my kind of evidentiary range of values. Now, why did I choose this? Well, it makes sense that the variability of my estimator would factor into this because p hat sub s minus p hat sub I is going to have some sort of variance. We know that from this result here. So factoring in the underlying variance, at least in terms of the standard deviation, makes sense. But where does the 1.96 come from? Well, I'm going to have to state some sort of a probabilistic guarantee about this interval. So what's the probability that I'm going to maybe contain this true parameter? Not for this particular interval, but if I was to run a large number of repeated experiments. And so if I want to contain maybe about 95% of the probability, then I need to contain about 95% of the probability under a standard normal. So this is a standard normal distribution. So if I go in here and I look, okay, so this is the probability of being between particular values. So between -1 and 0 is like 34.13%. It's symmetric, so it's going to be the same between 0 and 1. So if I was to go through and add up all of these percents, I would find that I would have slightly over 95%. And since that was from -2 to 2, we would think, well, if I make it just a little bit smaller, -1.96 up to 1.96, then I've contained this probability of my standard normal. And hence I get this kind of probabilistic guarantee for my confidence interval. Now, we really would want to talk carefully about how to interpret confidence intervals, but a good heuristic interpretation that you can use without getting yourself into trouble is this plausibility statement. Like, this is a range of plausible values that we have for this underlying population parameter. So like, which in this case is the difference between the two probabilities for each one of the groups. So something like 0.01 up to 0.03. So we've quantified our uncertainty in a different way, and we've given ourselves kind of this concrete range that has some sort of a probabilistic guarantee that's backing it. Okay, so given the experiment that was actually run, we can now take this and we can say, all right, we have evidence to suggest that we should use this services banner. And we'll find that, not surprisingly, this was a viable candidate at the end. But we missed just an absolutely essential first step before this was run. And that was, why did they pick 1 week and 2 week? How did they get this many users when they went to partition them into the different arms of the experiment? You have to talk about power, and you have to talk about deciding carefully what's the sample size that you're going to use for particular experiments before you actually run the experiments. It's an essential first step. So how do I know that I have a large enough sample? It costs money effectively to wait. You have to allocate users to these different designs. In the library experiment, it's not so like life or death, but it could be a huge deal in other applications. So the answer is going to depend on how large of a difference you'd like to detect. If you're satisfied with detecting a huge difference, like a 10% click-through rate versus a 1% click-through rate, you're probably only going to have to collect a few handful of observations to be able to detect that large of difference. If you want to detect a really small difference, like the click-through rate for services is like 1/10,000th higher than that for Interact, you're going to have to collect a tremendously huge amount of data before you can make that sort of a statement. So this isn't really a statistical question at this point. It's a business question at this point. Like, how large of a difference is meaningful for you to detect in order to make a change from Interact to services, to make a change from the existing drug therapy to the new drug therapy, to make a change from this ad to the other ad, whatever the underlying scientific question or application is that you're trying to use. So if we want to detect a small difference, which you would like to be able to detect in this case, it would take a huge amount of data, and hence we'd have to wait a really long time. So we have to kind of balance it as to what's a meaningful difference, but one that's still, that's large enough that would actually make an impact if we were to make that change. So, we could say there's 200,000 students in the student body. It doesn't really matter. And maybe we've sent out a questionnaire to some of the students asking them what kinds of things they would like to do on the library website. And then we've mapped that to the website, and we found maybe 6% of students really should be clicking on the Interact tab, say. And it seems like at this point, there's maybe, we think about 1% of the students are clicking on that tab. We think maybe 6% of them should be. If we were to maybe increase the number that clicked on that tab by like 1 percentage point, that would be like 200 more students getting, served in a sense, like more efficiently by the website. That would be like, I would say clinically meaningful, since I tend to work more on clinical trials, but that would be a significant, in a sense, difference enough for me to make this change. So that's what maybe I would decide if I was doing this particular experiment. Again, I haven't run the experiment yet, so I'm just doing this all from a pre-processing perspective. So back to the hypothesis test. The null hypothesis is the same, and the alternative hypothesis is similar. It's just a specific version of the alternative. We know the alternative is just that the difference is strictly greater than 0. So now I'm saying I want to detect a particular value of the alternative hypothesis. That would be 0.01 difference between those true probabilities. So now the question becomes, how large of a n do I need for each one of these groups in order to detect this difference? And just crucially, and I've said this a number of times, and mainly because, based on the way that I've introduced these ideas, I've done them in the wrong order. You have to do these types of calculations before you do your experiment. Otherwise, you can just only say what your experiment died of. And you're just doing, generally speaking, wasting resources. So I'm trying to say this multiple times. You're probably sick of me saying it by now, but it's so essential that it's worth repeating and repeating. So to discuss this further, we need the idea of power. So we're almost done, actually. There's only a couple more slides. So we just need to stick with this for another minute or two, and we can get to the kind of conclusion here. So we need to talk about power, and not just, it's not a general word. It's actually a reserved term inside of statistics. There's a variety of decisions that we can make. We can either, not reject the null, or we could reject the null. And that could be the correct decision in either case, or it could be the incorrect decision in either case. In this case, we know that the null hypothesis is false because we're positing that the difference is 0.01, which is not 0. So we want to talk about what's the probability that we're ultimately going to reject the null hypothesis. So we need to formalize this whole decision-making process a little bit more carefully before we can talk about this notion of power, which is an essential notion of how do we decide the minimum sample size that we're going to need. So we've already seen this result before. If the null hypothesis is true, then this ratio, p hat sub s minus p hat sub I divided by sigma hat, has a standard normal distribution. And that we saw it by having sigma squared over in this term, but we've just divided by the standard deviation. So that makes it a standard normal. Hence the term standard, by the way, and standard deviation. Okay, so we need to decide, when are we going to ultimately decide that the null hypothesis is not a reasonable or tenable assumption anymore? We're going to encode this via probability. So I did this with that kind of sampling idea earlier, and that was kind of trying to define this intuitively. Now we're going to define it a little bit more carefully via probability. So I said we're going to reject H naught, or just decide that H naught is not reasonable, if p hat sub s minus p hat sub I is large. How large does it have to be? Well, it has to be about as large as 1.65 times sigma hat. Once it gets at least as large as that, then we're going to say that it's too large for us to accept the null hypothesis as a reasonable assumption anymore. And the reason we have that is that there's some probability of exceeding this. In the previous example, we had like a 1 in 100,000. Now we're going to say, well, maybe a more reasonable standard is about a 5% chance that we've made the wrong decision in this case. So large values of, this shouldn't be absolute value, sorry. Just large in actual large, like positive values, larger than 1.65 indicate the null hypothesis is unlikely. That's the underlying idea. So using this main result, we have that the alternative hypothesis is actually true. So that's the actual underlying distribution that we're referring to. Correct decision would be to conclude that the null hypothesis is false. So power is just what's the fraction of time, or equivalently the probability that we make this correct decision. So we've decided that we'll reject the null if this ratio is greater than 1.65. So now we just need to say, how often are we going to exceed this 1.65 ratio, given that the true distribution isn't the null distribution, it's the alternative distribution, which has a different mean. It has a mean of 0.01 instead of a mean of 0. So we just need to correct our probability statement to say that we need to subtract off the mean. That's what we're doing here. And we just need to do the same thing to both sides. So we just subtract, I guess I'll include this in that ratio down there. So now we have the probability that a standard normal is going to exceed. So if this is a standard normal, looking at the probability that it's going to exceed 1.65 minus the ratio of the alternative to the standard deviation. So we'll have, maybe 1.65 here minus 0.01 over sigma. So think through what happens as sigma gets really small. So the variability goes down. We're going to detect this true state of nature with very high probability because there's almost no variability. Well, if sigma gets really large, or sorry, as it gets really small, this value, the 0.01 divided by sigma, is going to get really big. And we're going to subtract a really big number. And so this probability is going to go to 1. So that's the kind of intuition behind this power calculation here at this point. So we've really, we've described the entirety that we need in order to talk about power. We just need to say that sigma depends on n. Now we just described the relationship between n and this power and the sample size that we would need in order to correctly make the right decision, which is to reject the null hypothesis. So here's the final technical slide. Thank you for sticking with me. We'll kind of clean this up and talk about a few details here afterwards, but this is the punchline. So we have this questionnaire says that we think the underlying parameter is something like 0.01. This isn't an essential part, but it's just informing what I think is the correct or a reasonable magnitude of the difference I would like to detect. So I would like to detect this 0.01 difference. And so now I can say, what's the probability that I actually would reject the null, given that the null hypothesis is false? It's false in this particular way, that the alternative is true, and that P sub s minus P sub I is equal to 0.01. So this is the truth. So if I have a sample size of 10, so I just send 10 people to each one of these different websites, and this is that true value of the difference, I would only reject the null hypothesis about 0.054% of the time. So I would only make the correct decision in approximately 1 out of every 20 times I ran this experiment. So that's not very satisfactory. I could increase it to 100 and 100, and I would increase my probability to about 0.14. The general rule of thumb for power, and it's really isn't born out of anything, but this is what people tend to use, is trying to find a power of 0.8. That seems to be about the kind of like industry standard that people look for. So if I have a sample size of about 1,800 being sent to each one of these websites, I would achieve a power of almost exactly 0.8. Note that here's the power calculation done as this post-mortem of the experiment that was run. They did 1348 and 3714, and they ended up with a power a little bit less than 0.8. So if I took the exact same number of observations and I allocated them, instead of this kind of unequal split, I allocated them to an equal split, I actually could get a power approximately 0.9. So I could get much higher power with the exact same budget by just having a better experimental design here. So this is a depiction of power on the vertical axis. This top of the box is at 1, so that's the highest power can be because it's just a probability. So as n sub I and n sub s are small, like towards 0, we have a power that's very low, towards 0. And then it's going to increase towards 1 as we increase n sub I and n sub s. And the steepest rate of increase is if we actually keep those sample sizes equal. So doing that minor change and trying to balance our experiment is going to be the most efficient use of our experimental budget in terms of the number of users that we're allocating. All right, so the conclusion is that we could have run this experiment for a shorter amount of time, like in terms of the number of users, and gotten more power if we had done a more sensible experimental design by doing this pre-processing power calculation. So I want to look at a couple of websites. So the first one is one for doing these power calculations. You can either use R and using the framework that we just talked about, or we can use someone's applet. And then I want to go to this website, the actual library website. So bear with me for 1 second. All right, so here is it's a nice applet for comparing different for doing this power calculation for proportions. I'm just trying to make the text a little larger. Okay, so I want to calculate the sample size for a specified power. Enter the value for this P1. So we said that that was like 0.001. And then we would like to detect if this one was 0.01 more, so it's 0.02. I didn't describe the difference between a one-sided and two-sided test. We did a one-sided test. We picked that threshold of 1.65, which was corresponding to a 0.05. We saw that was that probability calculation. And then we needed to find our power. 0.8 seems to be the standard, although there's really nothing magical about that. And if I click calculate and find that, yes, indeed, something like 1826 would be the appropriate number of observations to allocate to each one of those treatment arms in order to detect a difference of 0.01 80% of the time, so with 0.8 probability. And then I just wanted to finish up with going to this current website. So this experiment was done some number of years ago, so the website has evolved a little bit over time. But if we scroll down, we'll see that there's been a new tab because the library has changed, but indeed the services banner was the one that was actually, I guess, the one that was actually chosen out of all of those different options. All right, so with that, I'll turn the floor over to you to see what kind of questions you have for me today.
Well, first of all, I wanted to thank you, Dr. Hamrighausen, for such a great presentation. For everyone in the chat, if you have any questions that you like to ask him, feel free to type them in the chat and then I will read them out to him, or you could come off mute and ask. Before you leave, I would like you to please fill out the quick survey that we have posted in the chat. It would really help us just gauge how this event has gone.
One thing that I can do is go and readdress a question that came up. I was a little bit heuristic about it when it came up, but how could we adapt this to the case where we were trying to compare all of those different options at the same time? So I'll delete a little bit here. But the main way that the adaptation would be, so we would do exactly what we just did here for each pair of the different options. So I guess, anyways, and so What we would need to do though is for each one of the pairs, we would be kind of trying to compare them or do this hypothesis test with a certain probability. So what we would want to do and what we would end up doing is we would need to increase this value. We need to increase this value. And this is to control for multiple testing. So the amount that we need to increase it is going to depend on the number of comparisons. So I think it was 5 comparisons. So that would be 10 different comparisons we'd be making. So we would need to increase 1.65 so that this equation still held, but with this probability being smaller. And in fact, 1/10 is large. That would be a sufficient change. So that would increase this value so that it was like 0.05, which I think would be something like 2.6. Don't quote me on that, but it would increase the value substantially. So what that would do would help control for this multiple testing sort of phenomenon. But and otherwise, everything would be exactly the same. It's very it's a very extensible technique. All right. Well, everybody is.
There's one question in the chat.
Oh, great.
So,
I'm sorry. I don't have it. Yeah, so type 1 and type 2 error are we've talked about here today. I just didn't actually use those words. So if we go back to what we did, so here's our decision. And here's like the truth. And let's say that the truth is that the null hypothesis is true or that the alternative is true. Our decision is to not reject the null or reject the null. So there's a 2x2 square, there's 4 possible options. So if we decide to reject the null, but the null hypothesis was true, we would be in this unfortunate square. That's what's known as a type 1 error. So I'll just write a 1 here to indicate that. And that's exactly, I'm gonna delete my adaptation here because it's gonna cloud this a little bit. But that's exactly what we did by choosing this threshold at the particular value, is we've decided that the probability of a type 1 error is equal to 0.05. So we're controlling for that in this particular case with this particular value for this threshold, 1.65. A type 2 error is to fail to reject the null hypothesis, even though the null hypothesis was false. So that would be this particular case for power. And power actually just resides in this happy little part of the table right there. So the diagonal parts are the ones we made the correct decision. So this is power. That's the probability that we were just computing here and trying to find a sample size to achieve a particular power. And it turns out that 2, the probability of a type 2 error, is just 1 minus p. So 2 equals 1 minus p, if you know what I mean here. Like I'm being symbolic. So we talked about actually all three of these notions in this slide. We just kind of did it a little bit obliquely. So if you're interested in talking about the type 2 error, it's just going to be 1 minus the power. So when we went onto this kind of like penultimate slide here, when we were trying to achieve a power of say 0.8, that means that we're by extension allowing a probability of type 2 error of 0.2, the complementary probability. So we would like the probability of a type 2 error to be small, which would mean that power would be large. But note the price. The price is we have to run our experiment for ever increasing amounts of time in order to achieve that. All right, so everybody is satisfied with their current body of knowledge that they've acquired. That's great. I thank you all for spending your afternoon with me. I feel honored to be a part of the Datathon. Good luck to you. And if you happen to see me in, in physical reality form at any point, then feel free to say hi. I would love to talk to you. So good luck and enjoy the rest of your weekend.
Will you also be available on Discord after this?
In a sense, yes. Yes, I will
Okay.
try to be. I'm not the most familiar with the Discord, but
Oh, it's okay. No worries.
yeah, I will try.
Okay, I think that's all the questions we had. Thank you so much again.
No problem. It was my honor.